Okay, so recapping. This is a lecture on Bayesian decision theory, which is kind of like an extension of probability theory. And so this is kind of like our first introduction to classification, right? So we spent a couple lectures talking about probability density functions, right? PDFs. So I see some training data and I build a PDF out of it, right? Like I build either a Gaussian PDF or last time we talked about building like a mixture of Gaussians PDF, right? So now suppose I've got labeled training data where I have some X's and some O's, some cats and some dogs, right? And so what I want to do is I want to build a distribution of the data that I see as a function of the class and then make a decision about which class I should be in, right? And so that's what we're going to talk about is Bayesian decision theory. And I'll say this again at the end, but if you're interested in this kind of thing, there is a whole graduate level course on extending these ideas, right? So there's a course called Detection and Estimation Theory that really kind of starts from this lecture today and then develops that over the course of many lectures in different ways, right? So here's the idea. We're trying to distinguish or design a classifier to distinguish between two classes. And so when I was a grad student, there was a classic book, Duda and Hart, on pattern classification, and their running example about this classification problem that they had on chapter 1 was distinguishing between salmon and tuna, right? They were thinking about you take pictures of a fish, you see how long the fish is, you see what color the fish is. If you're a sushi person, you can think about salmon and tuna on your plate, right? But basically the idea is that you're going to see an instance, a sample. And so there is what you call state of nature, which is a different way of saying, kind of like there's a ground truth. Each sample is one or the other. Either salmon or tuna, right? And so we may have so think about this like I used to think about this like fishing, now I think about like conveyor belt sushi, right? So, you could imagine that there is kind of like a pre-existing probability that the object is in class 1 or class 2, right? So we may have what's called prior probability over the classes. Right? That's like saying I have a probability that the object is class omega 1 and the probability that the class is omega 2 and that, these things have to add up to 1. One way of thinking about this is like a probability mass function, a PMF, over the class labels, right? So there are two possible outcomes. So now the next fish comes down the conveyor belt, and I have to make a decision. Is this salmon or is this tuna, right? So if I didn't actually, have any measurements, any features that I'm extracting from the fish, the best thing that I could do basically just say, okay, well, I'm just going to choose whichever one of the classes has higher prior probability, right? So say this is a restaurant that serves, 2/3 of its dishes are salmon and 1/3 of its dishes are tuna. Well, then the safe thing to do would be to just choose salmon every time, right? Choose the class with the highest prior, right? So that's called a decision rule. It's a pretty dumb decision rule, but that is a decision rule, right? So, without any additional info, we would choose the class with the higher prior, right? Whichever one of p omega 1 and p omega 2 is bigger, that's what I should choose, right? But of course, I'm always going to choose the same thing, which is kind of dumb. But this is called a decision rule. The decision rule tells me how to process the input and produce a classification, right? However, this is going to, of course, generate a lot of mistakes because I'm never going to classify as anything other than salmon, right? So if I had that case where salmon was 2/3 and tuna was 1/3, then I'm going to be making a mistake on the average 1/3 of the time, and my error rate is going to be basically 1/3, right? Obviously, it seems like I should be doing better, right? This is like a bad one, since we always make the same decision and have error rate or error probability of, whatever the minimum of these two numbers is. Okay, so obviously in the real world, we want to make our decisions based on data, right? And that's what this course is about, is learning from data, right? So the natural thing to do is to actually take some measurements of the thing that we see coming down the belt, right? That's called a feature vector, right? So, better thing to do would be to observe a feature vector it's called x, and decide based on that. Right? So if we had a number, for example, with salmon and tuna, we know that if we had some sort of scale of, where this side is orange and this side is red, that, salmon is more orange and tuna is more red, right? So I should kind of look at the fish, look at the color of it, and then decide what to do, right? That should play a big role in my decision, right? And so the idea is that based on the training data, I'm going to build a PDF over my feature vector for each of the classes that I have, okay? So the idea is, based on training data, for example, this is kind of like why I started with talking about density estimation, right? So we talked about ways of estimating like a Gaussian or multivariate Gaussian, right? So based on training data, we build what I would call class conditional PDFs like this. Little p of x given omega 1 and little p of x given omega 2. Right? So these are now kind of like, what is the probability density that I expect to see of x under each of the two classes? And just so, I know it can be a little bit confusing. It was certainly confusing when you teach probability. Usually what we're going to do in this class, and I'll try to be consistent, is that, little p means PDF. Big P means PMF or, probability. So usually in the kind of like discrete world, I'm using a big P, right? And in a continuous world, I'm using a little p. And I know it's kind of hard to distinguish which one I'm talking about on a piece of paper, but generally we're going to be able to understand it from context, I hope, okay? So these are called class conditional PDFs, also known as likelihoods, and that's an important word. Okay? All right, so the classic example, right, is if we're doing like kind of salmon and tuna, what I might have is, let's just imagine that I have some sort of one-dimensional feature, and I would say, okay, I have the, salmon distribution looks like this, and the tuna distribution looks like this, and this is basically my p of x given the class on the right. And so I can see that when this x number is low, salmon is much more likely than tuna. When x is high, tuna is more likely than salmon. And then there are a bunch of x values in the middle make each of the probability densities, could have done a reasonable job of generating that sample, right? So I'm going to make, some mistakes in this region, but I'm less likely to make mistakes at either side, okay? So I have these likelihoods, and then I have the priors, right? So again, when we talk about decision theory, we're trying to kind of combine the prior probabilities with these likelihoods, right? So say, for example, I had a sushi restaurant that was just like it's a salmon place, right? Like 99% of their dishes are salmon, right? Very occasionally a tuna thing comes out on the conveyor belt, right? Now coming down the conveyor belt is a red dish, right? I'm like, my priors are telling me that this is very likely to be salmon, but my likelihood is telling me that red things are tuna, right? So how do I trade off the prior probability, which is kind of agnostic, doesn't depend on the data at all, with the feature vector that I have? Well, this is what we call Bayes' rule, right? So Bayes' rule hopefully is one of the first things that you learn in a probability class. So how do we kind of make the right decision, right? So basically, we decide based on Bayes' rule. Bayes' rule basically says, like, the probability of, salmon given the feature is equal to the PDF of the feature given the class times the prior of the class over the PDF like this, right? So this is a different way of saying, saying this a different way. The numerator is staying the same. If I wanted to, I could expand out the denominator and say, well, what is the probability, what is the PDF of x? The PDF of x is basically a mixture between the two ways that I can get x. Either it's salmon or it's tuna, right? So the bottom part is actually expandable like this. This is also known in the bottom as what's called the total probability theorem, right? Also one of the first things we talk about in probability. That's like saying that, how can I get the probability of some event? Well, it is basically like the sub-probabilities of all the ways that event could happen times the probabilities of those events happening, right? So it's kind of like saying I weight the sub-likelihoods by the priors, okay? And then, so again, this is kind of like, again, another critical thing. This is called the posterior probability. So the key things are, again, this thing is called the prior. This thing is called the likelihood. And this thing is called the posterior, right? And so the whole idea of Bayes' rule is basically saying, before I saw anything, I had a prior probability of what I thought I would see, right? That's the P of omega 1. Now the fish comes down the conveyor belt, and now I have to make a decision about, like, how do I update my probability? That's kind of like saying I've updated my belief of which class it is based on seeing the data, right? So I'm kind of moving from this number to this number, right? Based on the data that I see. And so the Bayes decision rule is basically saying, I'll put this in a box. That's basically like saying, I choose if this thing is greater than this thing, then I choose omega 1. If this thing is the other way around, then I choose omega 2. And if on some sort of off chance they're equal, it doesn't really matter. I just choose either. All I'm doing basically is taking whichever one is bigger, okay? And so we can show that the good thing about Bayes' rule is it minimizes the overall probability of making a mistake, okay? So the key thing here is this minimizes the average probability of error. Okay. So really what I'm doing in Bayes' rule is I'm comparing the posterior probabilities of the two classes and choosing whichever one is bigger, right? And I can rewrite this a little bit, right? So if I kind of want to rewrite this rule, what it's saying is that, I can I can expand this stuff out with what's on the right-hand side here and move stuff around to say that, rearranging, the rule is to say, basically, if the likelihood here is bigger than this number, then I choose class 1, right? If it's not, the other way around. So the nice way of looking at it in this world is that this here, oddly enough, is called the likelihood ratio, because it is in fact the ratio of likelihoods. Okay. And so, the idea is that I'm comparing the likelihood ratio to a threshold, and the threshold comes from the priors, right? So for example, if tuna was much, much more likely than salmon, then this number would be really big, and it would be hard to overcome the decision of just choosing tuna all the time, right? On the other hand, if the ratio, if the priors were roughly equal, right? So if salmon and tuna were about equal, then this number would be about 1. And it would just be like saying, well, choose whichever one has a bigger likelihood at that point, right? And that's kind of an important thing too, which is to say that, if the priors are equal, then we're just choosing the PDF that has the higher likelihood at X. Right? So it's like saying, all things being equal, what I do is I look at this graph and I just decide which of these curves is bigger at my point, right? But if I have unequal priors, well, then I'm going to weight that decision by like how much bigger does it have to be to let me choose that curve, okay? So let me pause and ask. Any questions or comments about what I just said? Yes?
So if the priors, which is, that's the probability of, that's right?
These are the ratios of the priors, yeah.
Yeah, so if the priors are equal, then you just check which point on which curve is largest.
Yeah.
But then if they're not equal, then how does that weighting work then?
Well, so maybe one way to think about this is like saying, okay, so suppose that, so maximum likelihood, and so let me just say before I forget that this is, also called maximum likelihood decision rule, which we've already talked about in class, right? We were talking about maximum likelihood estimation. This is the same kind of maximum likelihood, right? So it's like saying that, okay, suppose that my point under consideration was, here, right? So I would draw my line and I would compare this number to this number, right? Well, here I would say that tuna is bigger. Under the maximum likelihood decision rule, I would choose tuna, right? Now suppose I told you that salmon was 3 times more likely than tuna, right? That might change your decision. And so what that basically says is that this number would have to be, or this number would have to be more than 3 times bigger than this number for me to make that decision now, right? So it's kind of like how much bigger do I have to be, right? Other questions? Okay. Quick show of hands. Is this a familiar concept from something you've seen before? Most people, but not everybody. If you haven't seen this before, then that's what my probability bites videos are for, is to go back and kind of just do a quick overview of Bayes' rule, decision theory, and so on. That's all in those YouTube lectures. Okay. All right, so let's take it a little bit further, okay? So more generally, what if I have more than 2 classes, right? So I got the whole sushi bar, right? I could have 12 different kinds of sushi coming down the pike. Well, the same idea applies, right? So more generally, if we have, C possible classes, then we have a set of prior probabilities from omega 1 to omega c, and we have a set of likelihoods, p of the feature given omega 1 to p of the feature given omega c. In the same way, we form the posteriors, which is basically the probability of omega 1 given the class. We form the posteriors in exactly the same way, and we choose, class I with the highest posterior. And the denominator of this, decision, basically, again, we can kind of say the probability of x overall is the sum over all the classes, the probability of seeing x given class I times the prior. Sometimes you see this called the evidence. But one thing that you should be able to observe is that, when I take the likelihood ratio, right, this number drops out of this test, right? So here, all I'm doing is I've got the likelihoods and the priors, right? So the posterior, even though to compute the posterior, I need the denominator, which is this thing, to compare the posteriors, the denominator is the same for everybody, so it doesn't make any sense to necessarily have to compute it directly, okay? So you can usually ignore that in many applications. Okay, so far so good. So now what I want to do is kind of generalize this idea to say, okay, we want to talk about what is a decision rule more generally, because we're going to be talking about decision rules for classification in different ways for the next, couple weeks, right? So coming back to this idea of a decision rule is a function, it's called alpha of x, that maps any possible x to a class in, the set of C possible classes. And so, more generally, what I'm going to kind of talk about is that, there could also be some sort of an external risk to making a choice, right? Even if the choice is supported by the priors and the likelihoods, right? So for example, I did a lot of work on kind of like airport security screening, right? So you go to the airport, your bags go through the x-ray machine, and then they often will call you out of line to pat you down or to look inside your suitcase, right? So basically, they're trying to make a classification for every bag, could this bag contain explosives or not, right? Now, obviously, it's very unlikely that explosives are in the bag, right? So the prior on explosives is very low. However, there is a huge risk in making the wrong decision, right? So if a bag that does contain explosives gets through the airport, then there could be millions of dollars of damage, right? So what I kind of have to think about is, are there numbers that I can associate with the costs or the risks of making a given decision kind of independent of the data and incorporate those into my decision rule, right? So for example, if I am, extremely reluctant to incur costs, then I'm going to make a lot of kind of decisions that maybe I should look at this bag for explosives, even though the odds are there's no explosives in that bag, but I have to check because otherwise my cost could be very high, my risk could be very high. So that's what I want to kind of talk about next, is what happens when we have these possible costs or risks, right? So we define a conditional risk of taking action, alpha I for a given x. Let's call that the risk. Okay. And so what we want to do in the Bayes world, the most general version of Bayes' decision rule is most generally the Bayes decision rule minimizes the expected risk. That is, I want to minimize the expected value of the risk I take, which is the same as saying I want to integrate over all of the possible x values the risk of a given decision rule. So this is kind of like saying, what is my overall expected risk? And really, this looks a little bit scary, but it's not actually that complicated, because it's kind of like saying, okay, there are only c possible choices that I can make for every value of x in this setup, right? I'm making one of c choices, right? So I can kind of boil this down to say, okay, all I have to do to make this as small as possible is to make the least risky choice I can at every possible x, and there are c possible choices I could make, right? So we'll say that this is minimized if we make this risk as small as possible for each x, and there are only c choices. So we can write that the risk of taking a choice alpha at x is like the sum over all the possible choices I could make. All right, so let me say it like this. This is like saying, the risk of choosing I at x, right? Well, how could that go wrong, right? That's like saying I could have some costs. So here, this is like the cost of choosing J. Oh, I'm sorry. The cost of choosing I when J is true. And then this here is the posterior probability of J, right? So this is like saying, what would the overall downside be of choosing I? Well, I have to look at the capital C possible states of nature, right? It could be class 1, class 2, class 3, all the way up to class whatever, right? And for each of those possible, situations, I have a set of basically C numbers. It says, what's my cost, right? So in the 2-class case, we have kind of like the cost of, normal bag versus explosive. In the multiple class case, I could have like kind of different, like I could have a 3x3 matrix or a 4x4 matrix depending on how many choices I had to make, okay? So this is kind of like easiest to understand when I have 2 classes, right? So let's go back to the 2-class case for a second. So this is basically like saying, okay, suppose I had these costs. So in the 2-class case, what I have are basically 2 by 2 ways that I have to measure things, right? So I have, C00 is saying that, class 0 is true, and I choose class 0, right? Or maybe I should, I guess now I'm in 0, 1 classes, sorry. I went from omega 1, omega 2 to zeros and ones just for the sake of this slide, right? So omega is true. So the other way I could have this is that this is like saying that, omega 0 is true, but I choose omega 1. The other way around is that omega 1 is true, and I choose omega 0, and then I have omega 1 is true, and I choose omega 1. And so a lot of times, if we're talking about just making a decision between, 2 classes, one kind of way of thinking about this is that 0 is kind of like the thing is not there, and 1 is like the thing is there, right? So for example, explosives, I could say that 0 is no explosives and 1 is explosives, right? That's like saying that usually 0 means nothing is happening, 1 means something is happening. So sometimes you will see, in what's called decision theory, you'll kind of see this called the null hypothesis, which is like saying, nothing happened. And this is called, the alternate hypothesis. Right, something happened. So in kind of like a detection world, this is kind of like saying, okay, so what's happening here, these are called basically true positives. Right? Something happened, and I told you something happened. My algorithm was correct. This is being correct in a different way. It's like saying nothing happened, and I told you nothing happened. And then the middle two are basically kind of the operationally important things in the real world, right? This is like saying, nothing actually happened, but I said it did, right? This is what's called a false alarm, or a type 1 error. Right? This is the guy at the TSA line patting you down, right? You're innocent, but he's, it's a false alarm, right? So we have to clear this false alarm. This one is called a miss, or a type 2 error. Right? So that's like saying someone didn't get patted down and then they blew up a plane, right? So that's bad. And so as a user, you have to put some weights on what the costs of these things are, right? So typically, in the real world, you don't really have to pay anything for making the right decision, right? So often, these numbers are just 0, right? You don't get any bonus for making the right choice, but you're talking about paying a cost, right? But we may say that, C01 is 2 and C10 is 100 or something like that, right? For example, yes, it inconveniences you to get patted down, right? So it costs something to the system, right? But the cost is much higher if you miss somebody going through the system, right? So you, as the TSA at the airport, have to decide kind of what level of false alarms am I willing to tolerate. So I mean, certainly, you can't get both of these things to be low at the same time, right? So like, I could just have the alarm going off all the time, right? Which would mean that I'd never miss anybody, but everyone would be pissed off because they'd be getting scanned all the time, right? Or I could say, well, the machine just never goes off, right? Then I don't have any false alarms, but also I also don't have any misdetections, right? So there's no way to get those things simultaneously. You're always trying to trade those things off, right? And so if I think about how to write the Bayesian risk in this 2-class case, then let's put it all together, right? The overall cost of a decision rule is basically like saying this. It's like saying we want a decision rule that minimizes the expected value of the kind of cost, which is the 4 ways that things can happen, right? I have, basically I'm choosing, I'm choosing H0 when H0 is true, times the probability that happened, plus C01, and I'll write this out a little more clearly. It's like saying choose H1 given H0 times the probability of H0, plus this. So it turns out that now, I can kind of decide, okay, what should I do? I can crank through the derivation, and I can find out that the test that I'm going to do resembles the likelihood ratio test, except it's kind of like a different thing on the right-hand side. So we can show, let me write this down on another piece here. So we can show that this decision rule is, I again have the likelihood ratio, and I guess I shifted, you're wondering where these H's come from. These H's are the same as the omegas. I just kind of like my mental shift into hypothesis testing, it's the same thing, hypothesis or class in this case. So again, I have this likelihood ratio, and I'm comparing it to some threshold. This is, again, the same thing I wrote a couple slides ago with slightly different notation. So again, this here is the likelihood ratio. And I'm comparing the likelihood ratio to some number. And that number is it's got the priors inside of it, and it's got the costs inside of it. And so the idea is that when I bring the costs into the picture, then the costs also will affect the threshold at which I have to compare the likelihoods, right? So that's kind of like saying, okay, well, suppose that I had, the same number, and I'm comparing it against here, right? So if I had, equal costs, right? Basically, if I said, okay, I don't care, whichever way you make a mistake, it's the same number to me, right? So if these numbers are both 0 and these numbers are both the same, then this whole term goes away, and it's the same as the regular rule without any costs. If I have equal priors, right, like saying, well, I don't really care one way or the other about which class it is, then this number becomes 1 the whole thing, and I'm doing maximum likelihood ratio, right? So that's like the kind of, taking it from the easiest case, which is maximum likelihood, to adding in the priors, to adding in the costs. Okay, so let me stop and ask questions or comments about that. So I think that I have time to do a example, right? So let me do one of the problems from my probability class last semester. So this problem basically had to do with distinguishing between llamas and alpacas, because I do a lot of going to sheep shows and stuff like that, right? So basically, we're going to see an animal. We have to decide whether it's a llama or an alpaca. They look kind of the same, right? But how can I tell what the difference is, right? So this is going to be like a worked example. Let's suppose that alpacas, I'm going to choose a feature which is basically how long their ears are, right? And so I'm going to suppose that the ear length for an alpaca is exponentially distributed with parameter lambda equals 1/2. And the parameter for a llama is going to be, an exponential distribution with lambda equals 1/3. Okay? If you don't remember what an exponential distribution is, let me remind you that basically this is like saying that the probability of x given alpaca, right? This is like the likelihood is 1/2 e to the minus 1/2 x for x greater than or equal to 0. So here I'm just writing down the exponential PDFs. Okay. And one thing to remember from probability is that the exponential distribution, the expected value of that distribution is 1 over lambda, right? So here, this is like saying the expected value of x under a is 2, and the expected value of x under under L is 3, right? So llamas on the average have longer ears than alpacas, okay? Okay. So now let's suppose that I, approach a pen of animals, and there are 50 animals in the pen. And I want to decide, okay, are these animals all alpacas or are they all llamas, okay? So let's say that we see, a group of 50 of the same animal. Okay, so I have basically a set of measurements, x1 through x50. And let's assume that the animals are IID, meaning that all the animals in the pen are the same type of animal, but they are totally independent from each other, right? So I just pick them, if I pick two at random, they have no correlation between them, right? Okay, so now I want to do basically, let's do the the series, right? So let's start with the maximum likelihood ratio, okay? So let's suppose that, say we measured the average ear length as 2.55. Okay, so it's kind of halfway between 2 and 3. Maybe more likely to be llama because llamas have longer ears, but I should do a quick numerical thing, right? So the first thing I have to do is say, okay, well, I need to compute the likelihood ratio, right? So we need the likelihood ratio, which is like, I want to look at, whether or not the PDF of alpaca given x over the PDF of llama given x is, greater than or less than 1, right? So I need to compute this number. And this is just a different way of saying, the PDF of x given a and the PDF of x given L, right? So, well, I have to look at these 50 numbers, right? So I can say that the top part, right, the PDF of x given a, I have to multiply all these, 50 independent PDFs together, right? So it's like saying I have, 1/2 e to the measurement 1 over 2 times 1/2 e to the measurement 2 over 2, 1/2 e to the measurement 50 over 2. So I can see this is going to be 1/2 to the 50th power over e to the, or times e to the 1/2 times the sum from I equals 1 to 50 of the xi's. And in the same way, I'm going to have the same kind of PDF for the llamas, except with a third instead of a half, right? So what does the ratio of these things look like? We want to know. So is, 1/2 to the 50th power. And again, I'm going to kind of rearrange things a little bit to say, e to the minus 1/2 times the sum of the x's. Is that greater than 1/3 to the 50th power of e to the minus 1/2 times the sum of the x's? The easiest thing is to take the log of both sides, right? So basically, kind of what I'm doing is I need to, make things easier because all these numbers are really small, right? So this number is like super small. This number is super small. I could also say I want to have minus 50 log 2 minus 1/2 times the sum of the x's. Is that greater than minus 50 times log 3 minus 1/3 times the sum of the x's? Moving stuff around, this is like saying, is the sum of the x's less than, I'm just going to do some quick math, 300 times log 3 minus log 2. Or a different way of thinking about this is the mean of the x's less than 6 times this number? This number here, if I compute it, is equal to 2.433. Okay? So finally I have a number, right? And this number, I told you in the problem statement, was 2.55, right? So it's like saying, oh, this number is less than that number, therefore I would choose llama. Right? This is bigger than than my threshold, okay? So a different way of saying this, right, which is harder to draw, is that, I am looking at kind of a ratio of two exponential PDFs, right? I've got the PDF of llama looks like this, and the PDF of alpaca would look like this, right? And I'm drawing a number here. My number is like 2.55, and it turns out that this curve is bigger than this curve, right? And the crossover point here, this number here, where they're both equal, is 2.43, right? So kind of below that point, I would choose alpaca. Above that point, I would choose llama, okay? Okay. So, questions or comments so far? Okay. So now let's suppose that I add in some priors, okay? So now let's suppose that I say, okay, I'm in a certain zoo and I have some sort of prior idea about whether I'm likely to encounter llamas or alpacas, right? So now let's suppose that that the probability of alpaca is 7/10, and the probability of llama is 3/10. Okay. So now, what is the Bayesian decision rule? And actually, if I'm being really precise, it might be more accurate to call this the maximum a posteriori rule. I guess technically the Bayesian decision rule is the one that includes all the costs, right? But we don't have any costs yet. So now, what would I do? Well, I would have to kind of compare the likelihood ratio to a different number, right? So just to set the problem up, this would be like saying we would need to determine if the, density under alpaca, like this, is greater than this number, okay? So I have to compare now to a different threshold. Before, this threshold was 1, right? Now, this thing here is going to be the same kind of like, hairy mess of the ratio of these things I had last time. In the same way, I can do all my log computations, right? So now, just to kind of like, write it like this, this is the same kind of statement. So this here I had from, before. Now this number is 0.7, and this number is 0.3. And so now the decision is maybe a little bit less obvious because it's like saying, well, even though that number is kind of like between alpaca and llama, I think that alpacas are more likely than llamas, right? So the kind of question is, how much bigger is that value, right? So we can do a derivation, ... to find out that now I have to decide, is the mean number here less than the same threshold I had before, but now my threshold is, changing a little bit. Again, this was like a homework problem, which takes a little bit of time to work out. And this number here is 2.534, right? This number here before was still 2.55. So it's kind of close, but not close enough to make the jump, right? So I'd still choose llama. But I can't just do it by visual inspection. I would actually have to compute the numbers to decide whether this likely ratio was above or below the necessary threshold, right? And then finally, the last way I could change the threshold was say, okay, let's suppose that I am, super, anxious to find alpacas, right? I don't want to miss any alpacas. So I want to be adding a cost that says, the cost of choosing, llama when it's actually alpaca, I want to kind of trade that off with the other one. So adding costs, say we, want to, not miss many alpacas. What I could do is I could say, okay, I'm going to let the, cost of making the correct decisions be 0. I could say that the cost of choose alpaca when llama is true. All right, let's see. So let's say this. Make sure I got this right. So this is like saying the cost of, scroll back to my costs for a second here. Right. This is like saying choose llama when alpaca is true, right? So here, I don't want that to happen. I want to say I really don't want to make that kind of mistake. I'm willing to make the other mistake where I evaluate more animals and I find out that they're, the wrong thing, right? So then I would eventually do this calculation and I would run it through again. Now I'm going to compare the likely ratio to the ratio of the priors times this ratio of costs. And so now, eventually I would kind of come down to the question about whether or not this sum was less than some even bigger number. And now I'd say, oh, now I am under that bar. So now I would choose alpaca, right? So the effect of kind of turning up the cost of not missing alpacas is that this number gets bigger and I'm more likely to make the alpaca choice, right? So again, I didn't do all the derivations here. If you want to make sure that you understand this concept, then actually doing the derivations yourself and making sure you come up with the same numbers as I did is probably not a bad exercise, right? Like I said, this to me is like a probability homework problem, so I'm not dwelling on it too much. Okay, so this is kind of like the capsule summary of Bayesian decision theory, especially just with like 2 classes. Now, like I said, there are other classes you could take that go into this kind of thing in a lot more detail, right? So, one thing that I'm not going to talk about too much is that there are kind of variations on the theme, right? So one variation is basically, extensions of this idea. There's something called the Neyman-Pearson test, which you will probably see in a machine learning textbook. The idea there is to minimize the miss or type 2 probability for a specified value of the false alarm or type 1 probability. So kind of operationally, you'd say, okay, look, I want to have 5% false alarms, right? That's how much I'm willing to tolerate for the people going through my airport. Now, given that I've nailed one of those down, what is the best I can do on the other type of error I could make, right? So kind of that's operationally a useful thing to do. Instead of just kind of like deriving a test and finding out what your false alarm and miss probabilities are, you instead fix one and then you derive what you can do in the best case on the other one, right? And this also looks like a likelihood ratio test. Okay, so you get the same kind of thing, it's just the threshold on the right-hand side is different, okay? The other thing that you might see in a detection estimation class is the idea of maybe you don't necessarily have a fixed PDF for both of the classes, right? So say I'm kind of doing like a situation where so I know that if nothing is happening, I have this one PDF. But if something is happening, I don't know exactly what the PDF is. I know it's like in a family, right? So the other thing that you could say is what's called composite hypothesis testing. That's like saying, under one hypothesis, I could say that the mean of my distribution is 0, and under the other hypothesis, I could say that the mean of the distribution is, greater than 0, right? So it's kind of like saying, I don't know exactly what the PDF is in the second case. I just know it's not 0. It's bigger than 0, right? So again, I'm not going to talk about this stuff because I've already kind of like, switched into this concept of hypothesis testing, which is kind of not exactly the same as classification for machine learning, right? So what I want to do is, if you want to learn more about this, you take the 6th level course in detection estimation, right? This is kind of like where it would go. But let's bring it back to a critical machine learning idea to round out the class here. So the critical concept that you're going to see in machine learning is called naive Bayes, okay? So, back to machine learning properly. we talk about what's called naive Bayes classification. Okay? Or the naive Bayes decision rule. So the naive Bayes decision rule is basically the same as the hypothesis testing we talked about all during class, under a special hypothesis that all the features that I see are independent, right? All features are independent, and you can also say that the priors come from the training data labels, right? So say, for example, I've got a 10-dimensional feature, similar to what you did in homework number 1, right? So the naive Bayes thing to do would be to say, okay, I'm going to try to build a PDF of, I want to basically build this posterior. So here, this is like saying, not D data samples, but I have a, D-dimensional feature. Maybe a better way to say this would be, I want to find the posterior given a vector of features. Okay, so this is like my feature vector. Right? We know that that is proportional to, again, this alpha is actually just simply proportional to the likelihood given omega 1 times the prior, right? Same kind of idea. This is my likelihood. This is my prior. And the naive part is that I'm going to, simplify this to say that each of these scalar features is independent of the rest. And I multiply it by the prior at the end, right? So this is the naive part. This is a simplification. Because in theory, these features could very well be like correlated with each other, right? For example, suppose that I've got a fish coming down my conveyor belt, and I could measure how long it is and how heavy it is, right? So I know that in practice, the longer the fish is, the heavier it probably also is, right? So in real world, the length and the weight are definitely not independent of each other. But the naive Bayes simplifying assumption would be to say, okay, I'm going to build a PDF on length, and I'm going to build a PDF on weight, and I'm going to assume that those two features are independent. You can see why in the real world that's probably not like a great assumption, but it is a super simplifying assumption, because now I have basically just like a bunch of simple PDFs that I can build, right? So let me write this here, just simplifying this more. This is like saying I have a product over the d-dimensional features of these, the dth dimension given this class times this probability, right? And so, the easiest thing to do, right, would be to say, okay, I'm just going to take my training data, and so, let's suppose I have a big matrix of training data where I have dimension 1 through dimension 10, right? And then I have, samples, from like 1 to 1,000, right? So what I would do to do a naive Bayes classifier would be, okay, I'm going to take all of these, scalar values for feature dimension 1, and then I'm going to, for example, build a Gaussian model to give me, mean 1 and covariance matrix 1. Or actually, since this is just a single thing, I have, this. So I'm basically building a Gaussian model just for that single scalar feature, right? So that would be the easiest thing to do, right? Just fit a Gaussian to every feature, and then when I'm using the posterior, it's very easy to compute this thing here, right? Now, it doesn't have to be a Gaussian. It could be like a, mixture of Gaussians, right? So it could be an exponential distribution. It could be whatever distribution you want, but the basic thing that makes it the simplest algorithm is that you're doing it independently for each feature, even though the features definitely may have some internal correlation, right? And the same way, this prior, right, basically could be something like, estimating as the number of training samples in class I over the total number of samples that I have, right? So if I wanted to get some guesses about the priors from the training data, I basically say, well, I'm just going to take what proportion of things were in class 1 in my training data, and that's going to be my prior for class 1, right? So that's like the easiest thing that you could do. And that's why it's called naive Bayes. Okay. Questions or comments? So you can definitely anticipate that I'm going to ask you to build the naive Bayes classifier for some data that I give you, right? And then tell me for a given like X, what is the thing? And we're going to talk in the next few lectures about like, okay, so then there are so what does that mean in terms of kind of coming up? Is kind of like how does a decision rule divide feature space, right? So another way of thinking about a decision rule is kind of like saying, I have a bunch of X's and O's, right? I train some sort of classifier, and one classifier like this may just basically draw a line through space, right? But there may be some situations where my feature distribution doesn't look like that, right? So like, for example, maybe my feature distribution looks like, like this. Like, is it possible to have a decision rule that goes like that, right? I can't separate those classes with a single straight line, but if I was allowed to draw a curved line, then I could do a better job of separating, right? So that's going to be something that we're going to develop over the next bunch of lectures is different ways, number one, of drawing a straight line, and then number two, ways that kind of correspond to this nonlinear partition of the feature space to make better decisions, okay? All right. Any remaining questions? All right, so I'm going to stop the recording.